Hi there. So these last four examples from section 3.4 are going to be more kind of AP type questions. We're looking deeper into what we've already covered in section 3.4. So in 3.4, we've already covered the bulk of it. So we've discussed concavity, the relationship between concavity and a function's first derivative as well as its second derivative. And we've discussed about where a function, the points at which a function changes concavity is referred to as a point of inflection, and how to identify where points of inflection occur. And then we've also talked about the second derivative test. So a method where we're using the second derivative in order to identify relative extrema in some kind of special cases where the first derivative would be equal to 0. So now we're going to look at some problems where we're going to examine a given graph. So this first example is we're examining the graph of a function. And then we're also going to look at some examples where we're given the graph of the derivative of a function. And we're also going to look at like a table that gives us information about some specific values for a function, its first derivative, and its second derivative. So this first example that we're going to look at in this video, we're given the graph of f of x, that the graph of f of x is defined everywhere on the interval from a to k. So that means that every value between a and k has an output for the function f. It does not state that the function is continuous. And we can see that it's not continuous at x equals to h. There would be a removable discontinuity at x equals to h. But it does look like it's continuous everywhere else. Before we answer the two questions that I have on here about points of inflection and concavity, we can see that the graph between a and k, the points that I've identified, or the x values for points that I've identified, are kind of special to the graph, right? Like something happens at those values. So let's check out each of these subintervals of the interval from a to k and discuss what's happening to the function f from a first derivative and second derivative perspective. So the first interval from a to b, if we thought about drawing some tangent lines to the curve here, so about there, there, so if we think about what's happening to the values of the slopes of the tangent lines, which would indicate what's happening with f prime, the first derivative, those tangent lines, well, at the beginning of the interval, the tangent lines are positive, and then it looks like they're starting off pretty steep, and they're becoming less steep. And it even passes through a tangent line that would be horizontal, meaning the slope would be 0, and it switches to be negative sloping tangent lines. So if we think about what's happening to the outputs of f prime on the interval from a to b, we could say that f prime would be decreasing on that interval, right? Like it would be going from, if we were to assign values to the slopes, we could think like going from 2 to maybe 1.5 to maybe 1.5, to maybe 1/2 or 0, and then into the negatives. So on that interval, we would be able to say that f prime is decreasing, which means that the slopes at the points on the graph of f prime would be negative, meaning that f double prime would be less than 0. And that matches with what we've discussed already about the relationship between concavity and the second derivative. So on the interval from A to B, f prime is decreasing, and f double prime, the second derivative, would be less than 0, would be negative. And if we look at this next interval, if I again think about drawing some tangent lines to the curve, okay, so reading from left to right on that interval, that first tangent line that I drew here is negative, pretty steep negative slope. And then as I move closer to C, so as I'm going from left to right, it looks like the slope is becoming less steep. So like if I were to assign a value to that first tangent line, I could say like that has a slope of maybe -2. And then this one would maybe have a slope of like -1/2. And then 1/2 and maybe +2. So the values of f prime would actually be increasing on this next interval. F prime is increasing, which means that f double prime would be positive on that interval. If f prime is increasing, the slopes of its tangent lines would be positive. So f double prime would be greater than 0. So that's the interval from B to C, and that makes sense with what we've already discussed, that when the second derivative is positive, the graph of the function is concave up, looks like a cup. And then if we move to the interval from C to D, so drawing a few tangent lines to the curve on that interval, it looks like those tangent lines are becoming less steep. All positive tangent lines on that interval, but they're becoming less steep, meaning f prime would be decreasing. And therefore f double prime would be less than 0. So that's from C to D. And then from D to E, pick a color here, we'll do pink. Drawing some tangent lines to give me a visual of what's happening to f prime and the values of f double prime on that interval. Okay, so on that interval, it looks like we start with some pretty steep negative sloping lines, and then they're becoming less steep, and then switching to positive. So we're able to say that f prime is increasing on this interval, and therefore f double prime would be greater than 0 on that interval, would be positive. Okay, and then 2 more intervals to inspect. Let's look at from E to H. Here we'll choose a color we haven't used yet. Drawing a couple of tangent lines. Okay, so they're negative sloping tangent lines on the interval from E to H, and it looks like they're becoming less steep. So like you could think of that first one as being a slope of like -3, and then going to maybe a slope of -2 or -1. So f prime is actually increasing on that interval. Therefore, f double prime is positive on this interval from E to H. And then from H to K, negative sloping tangent lines, so the first derivative would be negative, but would f prime be increasing or decreasing? So negative sloping, and then it looks like it's becoming steeper in the negative direction. So we would actually say that f prime is decreasing on the interval from h to k. And therefore f double prime is less than 0. Okay, and then just looking at this graph, we can see where f double prime changes sign, right? Where the graph changes from concave up to concave down, or concave down to concave up. So at B, it looks like there is a point of inflection. The graph changes from concave down to concave up, right? F double prime goes from negative to positive. At C, there is also a point of inflection. At D, the concavity changes, but there's no tangent line that can be drawn. And remember, our textbook requires there to be a tangent line at the point for it to be a point of inflection. So we would call D a cusp, and we would say it's not a point of inflection because no tangent line, because f prime, because f does not have a tangent line at x equals to d. Okay, no change in concavity at E, right? F prime is positive to the left. Sorry, F double prime is positive to the left and to the right of E. And then H, well, at H, the function is not differentiable. So, well, it's defined. So it's not continuous. Sorry, it's not continuous at H. So at H, x equals to H, the function cannot have a point of inflection. Okay, so now let's actually answer these questions. So state the points of inflection. We just kind of went through, but we also have to justify. So we can say that there is f has a point of inflection at x equals to b because f double prime changes from negative to positive at x equals to b. And then we can say that f has a point of inflection at x equals to c because f double prime changes from negative to positive at x equals to c. Okay, and then question B, which actually would have maybe been more helpful to answer first, but we're going to list the open intervals under which f is concave up or concave down. So concave up looks like a cup on the intervals from A to B. No, not A to B. B to C. D to E, e to h, because f double prime is greater than 0 on those intervals. And then we can say concave down looks like a frown on the intervals from A to B, C to D, H to K, because f double prime is less than 0 on those intervals. Okay, so that was reading the graph of the given function f. Now we're going to look at a table of values for a twice differentiable function f of x, which is continuous on the interval from -3 to 5. So f is continuous from -3 to 5. And then we're also given the values at those chosen x values, which look like the endpoints of the interval, and then one other value for f prime and f double prime. So questions A and B, I've indicated they are review from previous sections. So explain why there must be a c on the open interval from -3 to 5 such that f of c is equal to 6. This is asking about the existence of a function value. This question is asking about the existence of a function value on a closed interval, right? Because we're given the function is defined on a closed interval. And we're given function values at the endpoints of the interval. So we want to guarantee the existence of a function value, which means we need to think intermediate value theorem. And we need to state those preconditions for intermediate value theorem to apply, which have been given to us. So we can say that since f is continuous on the closed interval from -3 to 5, that's a requirement, and when we look at the function value at the endpoints, okay, so the function value at -3 is 0, and the function value at 5 is 7, right? F of -3 is 0, f of 5 would be positive 7. 6 is between 0 and 7, and therefore, by the intermediate value theorem, we are able to say that there's a value c such that that function value exists. So we said since f is continuous on -3 to 5, and you have to state the inequality, f of -3 is less than 6, and 6 is less than 5. So since f is continuous on the closed interval, and that inequality is true, by the intermediate value theorem, by IVT, there exists a value c, since they mentioned c, on the interval from -3 to 5, could use interval notation as well, such that f of c is equal to 6. Question B is asking, explain why there must be a w, a value w, on that open interval, such that f prime of w is equal to 7/8. This question is asking about the existence of a rate of change, the existence of an instantaneous rate of change. So we should immediately be thinking mean value theorem. And we are given the values of f at the endpoints. Therefore, we can calculate the average rate of change over the interval from -3 to 5. But we need to set ourselves up to be able to reference mean value theorem. So we have to say, since f is continuous on the interval from -3 to 5, the closed interval, and differentiable that's given to us. It said that the function is twice differentiable on that interval. So and differentiable on the interval from -3 to 5, the open interval. And let's find the average rate of change. I bet it's equal to positive 7/8. Let's see. So f of 5 minus f of -3 divided by 5 minus -3 would be equal to 7 minus 0 over 8. So 7/8. So therefore, by the mean value theorem, there exists a value W on the open interval, which if you want to use from -3 to 5, or you can use inequality notation, your choice. So there exists a value W on the open interval such that f prime of W would be equal to 7/8. Okay, question C is asking about concavity. Is f concave up or concave down at x equals to 2? Okay, well, we are given information about x equals to 2. Given information about x equals to 2. We're given the function value, the first derivative, second derivative. Well, f double prime of 2 would be 4. Since f double prime of 2 is positive 4, that means that it's on an interval that is concave up. So 2 is on an interval that is concave up. So we can say f double prime of 2 is equal to 4, which is greater than 0. Therefore, that's our justification. Therefore, f is concave up at x equals to 2. Does f have a local max, min, or neither at x equals to 2? Justify. Well, that's the second derivative test. You do not need to reference the second derivative test by name. I'm going to, though. Why not? You can say by the second derivative test. You don't need to mention the name, but you can. Just make sure if you are naming something that it's the correct name. So by the second derivative test, f has a local minimum at x equals to 2 because f prime of 2 is equal to 0. That part's important, right? F prime of 2 is equal to 0, meaning that 2 is a critical number. Second derivative test is plugging critical numbers that make f prime 0 into the second derivative to check the sign of the second derivative. So since 2 is a critical number and f double prime of 2 is positive, that means that 2 is on an interval that is concave up, looks like a cup, and therefore 2 would end up being the low point on that interval. So because f prime of 2 is equal to 0, that just states that 2 is a critical number, and because f double prime of 2 is positive. So that's how we know that f has a local minimum at x equals to 2. Okay, so that was interpreting a table. And then these last two examples are both given the graph of f prime. So given the graph of the derivative, we're going to answer questions about the function f. So this is the graph of f prime. So all the outputs represent slopes of tangent lines on the graph of f on the interval from 0 to 9. So we want to make sure that we are being very careful in how we're answering our questions and how we're interpreting the given graph. So question A asks us, on what intervals is f decreasing? Since we're given f prime, and f prime represents the slopes of the tangent lines to f, that means we want to know where f prime is negative. The intervals where f prime is negative will correspond to the graph of f decreasing. So it looks like on the interval from 0 to 1, so we could say 0 to 1 and 6 to 8. And the reason is f is decreasing on those intervals is because f prime is less than 0 on these intervals. That's our justification. And if we were being asked where f was increasing, then we would say from 1 to 6 and from 8 to 9, because f prime is greater than 0 on those intervals. Okay, the next question asks us, what values of x does f have a local maximum or minimum? Well, local extrema only occur at critical numbers. And critical numbers occur wherever the derivative is equal to 0 or undefined. On the interval from 0 to 9, f prime is continuous, right? Like we can see the graph is continuous. So really we're just looking for where f prime would be equal to 0 and where there's a sign change in f prime, which would indicate f changing from increasing to decreasing or decreasing to increasing. So we do need to state that our function f has critical numbers at 1, 6, and 8, and why that is, like how we know they are critical numbers. So we make this statement first because we're reading a graph. If we were doing work, like if we were given the equation of a function and we were actually doing the work to solve for critical numbers, that's one thing. That's justifying your critical numbers. But because we're reading a graph, or if you're looking at a table, you need to make sure that you are including justification for those values being critical numbers. So we would say that f has critical numbers at x equals to 1, 6, and 8. Because f prime is equal to 0 at these points. Or at these values. And it looks like f prime changes from negative to positive at x equals to 1, which means f would change from decreasing to increasing and would indicate a local minimum. So we can say there is a local minimum at x equals to 1 because f prime changes from negative to positive. At x equals to 1. We want to be very specific. You know what? That happens at x equals to 8 as well, right? F prime goes from negative to positive. So why don't we include, let's rewrite that. Let's say there's a local minimum at x equals to 1 and x equals to 8 because f prime changes from negative to positive we can just restate that, at x equals to 1 and x equals to 8, or at those points. And then there's a local maximum at x equals to 6, because f prime is changing from positive to negative, which means that f is changing from increasing to decreasing. So local maximum at x equals to 6, because f prime changes from positive to negative. And on what intervals is f concave up? Justify. Okay. Well, f is going to be concave up wherever f double prime would be greater than 0, which corresponds to where f prime is increasing. And f prime looks like it is increasing from 0 to 2, 3 to 5, 7 to 9. So it looks like there's 3 intervals where f would be concave up. F is concave up on the interval from 0 to 2, 3 to 5, and 7 to 9, because f double prime is greater than 0 on these intervals. All right, we want to talk about signs and sign changes as our justification. We can also think of this as f prime is increasing. When f prime is increasing, f will be concave up, and when f prime is increasing, f double prime will be positive, which indicates concave up. Okay, points of inflection. Well, we're able to see where f is concave up right now. So that means that these other intervals, these other 2 intervals, are where f would be concave down, because that's where f prime is decreasing. So it looks like at 2, 5, and 7, 2, 5, and 7 are where the concavity is going to change. So where we would have points of inflection. Notice that those are also the points where f prime would have horizontal tangent lines, right? Meaning that f double prime would be equal to 0, which corresponds to the possible points of inflection. So we probably should indicate what the possible points of inflection are. So where f double prime would be 0, those are the possible points of inflection. So f has possible points of inflection at x equals to 2, oh, I missed one, 3, 5, and 7, because at those values, f double prime is equal to 0. Okay, and we don't have an equation in order to to solve for those possible values, where points of inflection could occur. So we have to justify it by reading the graph and making that statement. Okay, so we can talk about F double prime changing signs. It looks like at 2 and 5, F double prime changes from positive to negative. So we can say that at X or F has points of inflection at X equals to 2 and X equals to 5 because F double prime changes from positive to negative at these values. And then we can also say F has points of inflection at X equals to 3 and 7 because F double prime changes from negative to positive. At these values. Okay, and then this last question is asking us to sketch the graph. So I've copied and pasted the graph of F prime, but we want to sketch the graph of F. So that means we're going to have to interpret all the information that we've collected about the graph of F prime, the graph of F from the graph of F prime. To do this, it might be helpful for us to reference the example that we did up here and like what the curve looks like based on the sign of F prime and F double prime. I'm going to copy and paste this to use as a reference. A little smaller. So that's going to be our reference. Okay, so I'm going to go on kind of these subintervals of F prime where it looks like things change, right? Like whether it's the sign of F prime or the sign of F double prime changing. I'm going to start looking at the interval from 0 to 1 to determine what F would look like. And we are given the F passes through the point 0, 0. We need that. And we're going to do a sketch that could be the graph of F. It's not necessarily going to be super accurate. 0, 0 is kind of our anchoring point here. Like we need to have at least one anchor point to go off of. Otherwise, the graph could be kind of anywhere in the XY plane, like up or down, I mean. Okay, so looking at the first interval from 0 to 1, it looks like F prime is negative. So F prime is negative, which would be either this part of the curve or up here, this part of the curve. Okay, for F prime to be negative. And then F prime is increasing from 0 to 1. Therefore, F double prime would be positive. So Down here, that curve is what the graph of f will kind of look like. So I'm going to draw a graph that's concave up. Okay. And then f is decreasing. Yeah, so it has to go down from that point. Okay. So let's go on to, how about from 1 to 2? So f prime is positive from 1 to 2, and f prime is also increasing. Therefore, f double prime would be positive. So f prime positive, f double prime positive, that would be this bottom right section. So the graph will end up curving up. And you don't know how far it curves up. Like I can make it go maybe to there. Or I can make it go to the point 2, 0. I don't know. And then from 2 to 3, f prime is positive, but f prime is decreasing. Therefore, f double prime would be negative. So f prime positive, f double prime negative would be this top section of the graph here. So the graph will change. It looks like change concavity. Okay. And then from 3 to 4, f prime is positive and f prime is increasing. Therefore, f double prime will also be positive. So the graph will change to be concave up again. It's this bottom section. Sorry, that's not between 3 and 4. That's between 3 and 5. So it'll be concave up. I don't know where that point is exactly. I just know that it goes to x equals to 5. Okay, and then for 5 to 6, f prime is positive. But f double prime would be negative because f prime is decreasing. So f prime positive, f double prime negative would be this section here. So that's just from 5 to 6. And then 6 to 7, f prime would be negative, and f double prime would also be negative because f prime is decreasing. So that would be this top right section. We'll curve down. Okay, and then from 7 to 8, f prime is negative, but f prime is increasing, so f double prime would be positive. So f prime negative, f double prime positive would be this bottom left section. So I'll switch to concave up. And then 8 to 9, the last subinterval there, f prime would be positive and increasing. So f double prime would also be positive. It'll be this bottom right corner. So it'll curve upwards. And again, I don't know where that point when x is equal to 9, I don't know where that point would be. The graph, this is a sketch of a possible graph. We only know that first point 0, 0. And then I'm going to save this last example as a warm-up for us when we get back from break. So these were just a few more examples, getting you thinking deeper about the first and second derivative and concavity and points of inflection.